Equilibrium homework. We're going to start with some definitions. I'm giving you a choice on the homework. On the quiz, you're going to be told what to define. So if you define equilibrium, I need to see an example. Show me how there is a reversible reaction, how they're both occurring at the same rate, and give me a collegiate definition. Why aren't pure liquids and solids used in the equilibrium expression? Explain to me why a liquid and a solid's concentrations are not used. What is the difference between the reaction quotient and the equilibrium constant? Well, the reaction quotient is going to occur at any point during the reaction, but an equilibrium constant will only occur once the system reaches equilibrium. So explain those things to me. Provide an example if you can. Number 2, write the expression for the reaction quotient for the following reaction. You're expected to use the text editor. So let's start here because this question actually has several parts. So we're going to use the text editor. We were asked to write the reaction quotient. Now the reaction quotient is called Q. You can put QC for the concentration reaction quotient. And we need to start with the products. So our products, and you can copy, that's okay. We're going to start with NO2, close the bracket, and then we need to superscript. We need to superscript our coefficient there. We could use, and they're all gases, we could use QP instead, in which case we would use the partial pressures of each of these compounds. But I used QC, so I'm going to use the concentrations. Either one is correct, but you do have to show the superscripts. So the second part of our question, write the expression for the equilibrium constant for the following reaction. And is Kc greater than 1, less than 1, or approximately equal to 1? Explain your answer. Well, here, and I've inserted the Qp as well, just so you can see that. Now we're asked for the K. So the equilibrium constant K is going to be the product of the concentration of our products divided by the product of our reactants. And I'm using product here both in the chemical and the mathematical sense, but this is our K here. We have just the coefficients of 1 for our stoichiometric coefficients, so we don't have any superscripts in order to show. Now we don't have a concentration for our solid, because as long as they're solid, it doesn't change. Now our K value is going to be less than 1, and that's because the calcium carbonate, and you would need to type this out, the calcium carbonate is considered insoluble. And we know that because the solubility rules are given to us right here, just in case you need them. So compounds contain carbonate. Calcium carbonate is considered insoluble. There is a small amount of the ions in solution though, and that's given by this expression. So the K is much less than 0. So we know we have some small amount of our stuff. So let's just say we take this small amount and we set that equal to the concentration of our calcium. So if we have that, then our K value is going to be this value times itself, and that's going to be a much smaller number. So you see, it's a very small value. Number 3, for this reaction, the concentrations before equilibrium are reached are these values here. I'm just going to copy these over. So what's the value of the reaction quotient at this point? So let's take this information. First, let's write out our reaction quotient formula. So we have our QC is going to be equal to the concentration of our products squared divided by the concentration of our reactants, or the product thereof. So now I'm going to fill in the numbers that I was given. So the SO3 value, it's an 039, that needs to be squared. Divide that by my SO2 value, that is multiplied by my oxygen value. Now make sure you're putting these things into your calculator correctly. So we have 0.039 squared divided by the product of, and I'm putting these things in parentheses. 0.067 squared times 0.304, and I get a value of 1.11. Notice our sig figs, we have 2 sig figs in each of these. Are we given? It says report to the ones, to the tenths place. So 1.1 is what I would report. Number 4, initial concentrations or pressures are given. Here we have some concentrations. So we're going to calculate the reaction quotient and we're going to determine which direction the system will go. So let's see, we have our reaction quotient Q, and we're going to set this up. This is actually the opposite of the last problem we had. You might see a little bit of that on the quiz, times this value here. And then I'm going to plug in the values that I have. So SO3 is 0.5, and that needs to be squared. SO2 is 0.10 squared, and oxygen 0.10. So the value of my QC, when I put all that into the calculator, I get 4.0 times 10 to the negative 3. Now my QC is smaller than my KC. You see the KC was given to me, and I brought that over. That's right here. So because the QC is smaller, that means we need to make the QC larger, and we make the QC larger by increasing the concentration of our products. So we need to push to the right towards the production of more products so that our QC will come closer to our KC. So to enter this, the value of my QC, I'm going to enter 0.004, and then the direction the system will proceed. I'm told my options are left, right, or no change. This one's going to go right. And number 5, the value of an equilibrium constant for this reaction is 4.1 times 10 to the negative 4. We're asked to find the concentration of an equilibrium mixture with air at 1 atmosphere of pressure, and then we're given some concentrations. So that air value is actually information I don't really need for this calculation, but I am going to need these concentrations. So I'm going to move these over, and then we can work on this problem. So first thing I'm going to do is write out my reaction. So I'm going to have my N2 plus O2 reacts and reacts back to form 2NO. Now initially I have 0.036 moles per liter, capital M molar. I'm going to leave that off for now. And I have 0.0089, same unit, molarity, of my oxygen, and I have none of my product. Then it's going to change. So I'm going to take some amount X away from each of my reactants, and I'm going to add 2X to my products because of that stoichiometric coefficient. So at equilibrium, I have 0.036 minus X for my N. I have 0.0089 minus X for my O, and my NO is going to be 2X. So now I need to set up my K expression, and I have the concentration of my product squared divided by the concentration of my reactants, and that's the product of my reactants. So I'm going to fill in what I know, and what I know is what I figured out here. So I have my 2X squared and these values. And that is going to be equal to the value that was given, 4.1 times 10 to the negative 4. Now, looking at these values, I don't think I can simplify this because it doesn't meet the times 1,000 rule. So I'm going to have to work this out and use the quadratic expression, the quadratic formula. Now remember, when we're squaring this value, we're squaring both of these factors. So 2 squared is 4, and then x squared is x squared. So that's how we go from 2x in parentheses squared to 4x squared. That's actually a very common question that I get. So I'm going to set this up this way. So 4x squared, I'm going to multiply both sides by the denominator. And I've actually worked out what that denominator is. So here I've worked out the algebra. So all I've done is I've expanded this. Remember, FOIL. First, you multiply your firsts, your outsides, your insides, and then your lasts. And then I get this business here. That this becomes this. Then I distribute, so I multiply this through each of these pieces, and then I move everything over to this side. Now, you notice I have 4x squared on both sides, but I had this x squared here. And the reason for that is 4.1 times 10 to the negative 4 x squared. And I take and I subtract that from 4x squared. You're not going to feel it. You're just not going to see it. It's such a small number. So I simplified that part. And then equation, at least I used my calculator for that. If you know how to use your calculator to solve the quadratic equation, then please do. And I found then x equals 1.789 times 10 to the negative 4 molar. Now, remember, this is not the answer. This is x. And x is not the concentration of NO, which is what we're looking for. We're looking for the concentration of NO, which is 2x. We found x. So the concentration 2x, which is equal to 2 times 1.789 times 10 to the negative 4, capital M molar, which is going to be 3.62 times 10 to the negative 4, capital M molar. So here is a case where if you don't have time, just enter in the answer. You can always come back and fill in at the end if you end up with time. Or you can use the file upload assignment area to send me your work. Do not email me your work. Do not send it with Canvas message. Use the appropriate assignment submission.